The periodic table functions as a structural blueprint for human technology. Nowhere is this more apparent than in a single vertical column, Group 14. This is the carbon family, a group consisting of carbon, silicon, germanium, tin, lead, and the synthetic element Flerovium. Elements at the top of this group provide the highly rigid, insulating structures that form the foundation of biological life. Lower in the column, the same geometry yields the semiconductors used in artificial intelligence and the heavy metals required for radiation shielding. These diverse macroscopic properties are the mathematical consequence of a shared subatomic geometry. This Bohr model shows the baseline structural configuration shared by every element in Group 14, the ns2-np2 valence shell. Each atom possesses exactly 4 valence electrons available for bonding. By tracking how increasing atomic mass interacts with this specific 4-electron geometry, we can map the material constraints that dictate human technological evolution. We begin at atomic number 6, carbon. Occupying the top of the column, carbon has a uniquely small atomic radius. To maximize bonding potential within this tight space, carbon's 4 valence electrons reorganize through sp3 hybridization. This 3D vector model shows an expanding sp3 hybridized covalent lattice. This geometry forces atoms into a rigid tetrahedral network. These incredibly short, tight bonds require immense energy to break. This locks electrons, making pure carbon a powerful insulator. This geometric predictability provides the exact structural backbone required to build complex organic molecules. The architecture of biological information storage relies directly on this predictable covalent bonding. Looking at this physical molecular model, the complex double helix of DNA maintains its integrity because of the rigid geometry anchored by its carbon bonds. Carbon's small radius and unyielding electron grip provide the tight architectural anchor required to sustain biological life. Descending to silicon at atomic number 14 and germanium at 32, we see an increase in the principal quantum number. This animated comparison scales the atomic radius from carbon to silicon to germanium. As the valence shell is pushed further from the nucleus, the physical distance between the core and the outer electrons increases. At these greater distances, the valence electrons experience increased electron shielding from inner orbitals. This weakens the covalent bonds holding the lattice together. This energy level diagram illustrates the band gap, the energy required to kick an electron out of the structural valence band and into a freely moving conduction band. Because the larger atomic radius in silicon and germanium weakens their bonds, their band gap shrinks compared to carbon. It drops into a range where conductivity becomes conditional. This creates a semiconductor. By applying a specific voltage, engineers can modulate conductivity, turning the material into an electrical switch that alternates between insulating and conducting states. Silicon's conditional conductivity makes it the ideal material for etching microscopic logic gates and processing data streams. Digital logic is physically embedded in this subatomic geometry. Looking at the exposed internal gold die of this ceramic microchip, you are seeing the material manifestation of the digital world. Germanium's slightly larger radius provides higher electron mobility and a distinct refractive index compared to silicon. These refractive properties enable total internal reflection, making germanium a key component in guiding light signals through fiber optic cables. Germanium's narrow band gap also renders it transparent to infrared wavelengths, which drives thermal vision technologies. High-speed internet and the processing power of artificial intelligence rely on the natural band gaps found strictly in this middle section of Group 14. Expanding the atomic radius transforms the group's behavior, moving from the rigid scaffolding of organic life into the modifiable logic states of the digital world. Further down, we reach the heavyweights, tin at atomic number 50 and lead at 82. These atoms contain massive nuclei and deep, dense electron shells. This orbital visualization demonstrates the inert pair effect. At these extreme scales, 2 of the s orbital electrons stabilize deeply and refuse to participate in chemical bonding. Without 4 distinct valence electrons actively sharing bonds, the rigid tetrahedral covalent network seen in carbon and silicon collapses. The elements transition to metallic bonding. The remaining outer electrons delocalize, forming a freely moving, conductive sea around the atomic nuclei. Metallic bonding dictates tin's physical behavior. Because it is highly malleable and melts at a low temperature, early metallurgists could cast the durable tools and weapons that characterized the Bronze Age. Tin continues to serve as an easily melted connective metal today, acting as the solder that physically bridges components inside advanced supercomputers. Lead takes the transition even further. Its defining characteristic is extreme atomic mass packed into a dense metallic structure. This density provides a physical barrier to high-energy particles. We rely on heavy lead casings, like the massive industrial cylinder shown here, for industrial-scale radiation shielding. Lead's specific electrochemistry and metallic conductivity also allow it to facilitate heavy power cycling, as seen in the heavy casing of this car battery. At these atomic masses, Group 14 abandons delicate covalent geometries to produce the heavy, malleable shields and conductors required for energy storage and safety. At the absolute bottom of the column is element 114, Flerovium. At this mass, the nucleus exerts such an immense pull that the innermost electrons travel at near light speeds, introducing severe relativistic effects. These velocities warp the spatial shape of the electron orbitals. As a result, flerovium is highly unstable and can only exist synthetically for fractions of a second. Synthesizing flerovium allows physicists to probe the extreme limits of atomic structure and chart the theoretical island of stability in nuclear physics. Flerovium represents the breaking point. Under the weight of its massive nucleus, the structural rules that govern the rest of the carbon family finally shatter. This heat map shows a downward trend in ionization energy from top to bottom. It maps the group's chemical transitions from covalent insulator to semiconductor to metallic conductor. This spectrum is driven by the constant battle between a stable valence shell and an expanding atomic radius. Compare the extremes. The same electron geometry that constructs the scaffolding of DNA also yields the heavy plates of lead shielding. By tracking this periodic trend, we can deduce logical physical outcomes directly from subatomic data. The physical behavior of these 6 elements reflects the material constraints of human progress. The tools of the Bronze Age, the high-speed fiber optic era, and the logic gates of AI are all grounded in the shifting properties of this single chemical family. Mapping the carbon family provides the ultimate proof of how subatomic physics dictates the boundaries of human innovation.